All right, so let's really quickly kind of go through what are the possible scenarios for adding numbers together, bits together. So let's see, I can add 0 and 0, and I'll get an output of 0 and a carryover of 0, right? If I have 0 and 1, I'll get an output of 1 and a carryout of 0. If I add 1 and 0, the same, I'll get an output of 1 and a carryover. I should be consistent. We're going to use the term carry out from now on instead of carry over, and you'll see why in a minute. And then if I have 1 plus 1, I'm going to get I'm going to get an output of 1 and a carry out. I'm going to get an output of 0 and a carry out of 1. All right? So these are all the possibilities. What we could do is represent this information as a truth table. Let's say that this is P and this is Q, right? We can do our P and our Q. And we have for our outputs, we're going to call them S for sum and C out for carry out. So, and our possible inputs are 0, 0, 0, 1, 1, 0, 1, 1. Okay, so for 0, 0, the sum is 0. For 0, 1, the sum is 1. For 1, 0, the sum is 1. And for 1, 1, the sum is 0. For C out, they are all 0, except for the last case where carry out is 1. Makes sense? This is, this is how we apply those truth tables we were studying in the last section. Now, the question is, how could we represent this as a circuit or as a Boolean equation? Okay, so in terms of Boolean equations, we could write this as S equals, it is 1 when P is 0 and Q is 1, or vice versa. So the most correct way to say that is P exclusive or Q, right? If exclusively P or Q is 1, then the output is 1. Otherwise, the output is 0. For C out, that one is P and Q, right? We were using that and symbol there. We could draw this as a circuit to have input P, input Q, and we typically draw an XOR gate, and this is an OR gate, and when we add, it looks kind of like a Star Trek communicator. I'm not very good at drawing, you might notice. When we add the little half moon there, that becomes an XOR gate. So P goes into that, Q goes into that, and then the output goes to S. And then an AND gate is kind of a little bit of a round mushroom. So P and Q goes into C out. All right? So these are 3 different ways of representing exactly the same information. A truth table, a Boolean equation, and a circuit diagram that all do exactly what we were just doing with our Boolean addition. And all of these together are what we call a half adder. Why is it a half adder? Think about it for a second. We have a sum, we have a carry out, but what's missing from when we do Boolean addition? There's no carry in. So let's expand what we've been doing to include a carry in. All right. So now we've added cin as an input to our adder, and that's what takes it from a half adder to a full adder. Other than that, this is going to look exactly the same as before. Only now, in addition to these 4 possibilities, we also have 4 more possibilities for when cin is 1. Okay. Now, if all of them are 0, then sum is 0, and our carryout is 0 as well. If we only have 1 here, then our sum is 1, our carryout is still 0. Our sum is 1, our carryout is 0. Now in this case, this is the case we had before where our sum is 0, but we carry 1 out, right? Because 1 plus 1 is 2, and that's how we represent it. In this case here, what are we going to do? Well, if you're carrying in 1 and you're adding 0 plus 0, you're going to get a sum of 1 and a carryout of 0. Here we have 1 plus 1. We're going to get the same result we got up here. A sum of 0 and a carryout of 1. A sum of 0 and a carryout of 1. And in this case, where we have 1 plus 1 plus 1, that's where we have a sum of 1 and a carryout of 1. So this should correspond to what you're thinking in your head a binary addition looks like, right? So let's kind of walk through an example here and show you what I'm talking about with binary arithmetic and how it relates to the truth table. So if I have 1, 0, 1, and I'm going to add, I'll do 1, 1, 1. 1 plus 1 with, when we start off, the carry-in is going to be 0, right? Because there's nothing to the right of it. So there's nothing to carry in. So if we look over here, that's going to correspond to this line on the truth table, which means we have a sum of 0 and a carryout of 1, which means we're going to get 0 and a carryout of 1, which becomes the carry-in of the next entry, right? So here we have a carry-in of 1, a p of 0, and a q of 1. So we go down here, and that's going to correspond to this line right here, which again is going to give us a sum of 0 and a carryout of 1. And here we have a carry-in of 1, a p of 1, and a q of 1, which corresponds to this final line down here, which means we get a 1 with a carryover of 1, which results in an overflow in this case, and that's fine. So do you understand how this truth table, or I'm asking you. So I hope at this point you understand how the truth table corresponds to the mathematics. If not, we're going to come back. We'll be able to take a look at this in more detail in class. All right? So now we have 3 inputs. We have cin, we have p, and we have q. And their corresponding lines. And we still have our 2 outputs, S and C out. Okay, so to go back to our Boolean expressions, S, let's take a look at our table here. So S is 1 in any of the cases where there is only one input that is 1. So really, we could say P exclusive or Q exclusive or Cn. Right? That is the correct expression that demonstrates when S is true. Cout, go ahead and pause this video for a second. Take a look at Cout and see if you can find the pattern. Well, if you're thinking that doesn't seem like there are any easy solutions, you're probably right. But at the very least, remember our min terms and max terms. So you could always say P and Q and not Cn, or Cn and Q and not P, or etc., etc. So you could always do that. I will tell you that results in a very, very, very long, complicated Boolean equation that reduces down to this. P and Q, or excuse me, not P and Q, P exclusive or Q, not and Cn, so then we add the not, and then those two clauses are anded together and the whole thing is negated. So it's kind of, yeah, it's not very simple looking, but when we actually draw it out, it's much easier to see as a circuit. Let's do a couple of exclusive ORs. So again, P and Q come into our exclusive OR, and then we have another exclusive, another exclusive OR, and Cn, and the output of that exclusive OR goes into that, and that is S, right? So that's what we did up there. And then this monstrosity is not nearly as complicated as it seems, because here we have our P exclusive OR Q, right? And this is our AND gate, and we add a little dot at the end to indicate the not. So it was P exclusive OR Q NAND Cn. I'm drawing over things, but you get the idea. And then another, P and Q come into a NAND gate down here. And then both of those together, you see, go into another NAND gate that comes out here. And it's poorly drawn, but technically correct. And remember, technically correct is the best kind of correct. And what we really wanted to see here is how does the actual addition that we do translate into Boolean equations and into circuits. And these circuits are what are actually implemented in a computer. And we get into this again in much more detail in CS61 next semester. Okay. Now, instead of drawing out that entire circuit every time, usually we would draw it more like, P and Q, and then Cn, C out, and then S for our sum. So let's stick with that kind of format, and let's say that I have P and I have Q and they're coming in here, and let's say that I'm going to connect this to just 0. 0 is coming in on Cn for this first one, and then we have my sum out, and I have a C out here. Suppose I connected that to another full adder with a P and a Q and a sum and another C out, and suppose I connected that C out to the Cn of the next adder, and a P and a Q, and on down the line. What do I have here? I have a 4-bit adder, right? I can take two 4-bit numbers, P and Q. So really what I'm saying here is that this is P sub 0 and Q sub 0, Q sub 1, P sub 1, Q sub 2, P sub 2, Q sub 3, P sub 3. So if I had, if P was 1, 0, 1, 0, and Q was 0, 0, 0, 1, each of these corresponds to one of these adders here. And obviously on the least significant bit, there's no carry in, so we tied that to 0. And then the carry out of this bit becomes a carry in of the next one on down until we get to the end. And over here we have a carry out that really signals an overflow. If we hit that, the processor should handle it as an overflow. But that is exactly how you make a 4-bit adder. And you just continue that process to make an 8-bit adder, a 16-bit adder, 32-bit, 64-bit. It's the exact same thing. It's that same basic circuit that we just created repeated over and over again. So I hope this really ties together all the stuff that we've been doing so far, and this is kind of the conclusion of our number systems portion of the first chapter. Again, if you have any questions, ask them in the forum, and we will be doing some worksheets on this in class this week. All right? Good job.